Here's another problem. Suppose we're interested in the temperature T as a function of three variables, x, y, and z, at a point on a sphere in space. So, x, y, z would be the coordinates of a point on the sphere. And x, y, and z variables, each one of those is a function of two variables, r and s, such as longitude and latitude, or who knows, maybe you could even put elevation in there or something, like maybe it's just lines of latitude and elevation. Anyway, the chain rule describes this, is here. It says theorem 13.7, for two independent variables and two or three intermediate variables, suppose t equals f of x, y, z, and x is a function of two variables, r and s, y is also a function of two variables, z is a function of two variables, and if all four functions are continuous and have continuous first partial derivatives with respect to all their independent variables, then t has partial derivatives with respect to r and s given by dt dr is the partial of t with respect to x times the partial of x with respect to t, or sorry, with respect to r. Notice the dx's sort of cancel. Dt dy times dy dr. Notice the dy sort of cancel. And dt dz times dz dr, and again the dz's sort of cancel. The partial with respect to s, same sort of thing. So if t is a function of only two variables, knock off the last term. So this one and this one don't count. So what number was that? That was 13.7. Well, 13.6 allows us to adopt a different approach to implicit differentiation, which is nice. Suppose the first partials are continuous and the equation f of x, y, z equals 0 defines implicitly y as a differentiable function of x, say y equals some h of x. Since x is also a differentiable function of x, duh, now w equals f of x, y is a function of differentiable arguments x and y, so the conditions of 13.6 are met. So dw dx is dw dx, or partial of w with respect to x times dx dt plus partial of w with respect to y times dy dx. Sorry, I said dx dt. I meant to say dx dx there and dy dx there. Now, I don't know if you see what this leads to, but of course dx dx is 1. And now this can be solved. Actually, before we even solve it, notice that, remember, it was defined f of x, y equals 0. So dw dt is also 0. The derivative of this is 0 since the function itself is 0. And then this can be solved for dy dx. And so it looks like this. If we solve for dy dx, we could subtract this from both sides and then divide by this. And if you do, you would see that dy dx is the partial of w with respect to, the negative actually, of the partial of w with respect to x divided by the partial of w with respect to y. So we could say negative of fx over fy. And that's a different way from implicit differentiation as done in Calculus 1. And so that should make some problems that were originally very hard into problems that are easier. There's another theorem, the chain rule, applied to implicit differentiation. It's a theorem if the equation f of x, y equals 0 defines y implicitly as a differentiable function of x, then dy dx equals, well, we already derived that. So proof is written up above it. And if you got more variables, it behaves just like you expect it would, which is kind of good. So here's an example. And this would be maybe a bear of a problem in Calc 1. It says find dy dx at the point x equals 0, y equals ln of 2 for the equation x times e to the y plus sine of xy plus y minus ln of 2 equals 0. And I checked it out, it actually does. Painfully, but it does. So, in order to find dy dx, in calculus 1 we'd have to differentiate this, which would require the product rule, and when we took the derivative of e to the y we'd have to multiply by an x or dy dx. We'd have to use the chain rule on this one. When we took the derivative of x times y, we would have to multiply by dy dx. The derivative of this is just dy dx. The derivative of this is 0. We then have to solve that equation for dy dx. But now this is nice. Find the partial with respect to x of this. Of course, that's easy because e to the y is a constant, so it's e to the y for the derivative of this term. And derivative of sine of xy, remember y is considered a constant now, so it's cosine of xy, but then times the derivative of the inside part. Well, if that was 2x, we'd have an extra 2 multiplier, but it's y times x, so we get an extra y multiplier there. And the derivative of this, with respect to x is 0, the derivative of this is a constant, so that's also 0. So the derivative with respect to y, okay, well the derivative of e to the y is e to the y times the constant x in front, plus the derivative of sine, of course, is cosine, but this is a sine of x times y, so the constant x would be a multiplier, and then the derivative of y is just 1. So now, what is dy dx? It's the negative of this over this. And so here it is. And if you evaluated it at the point where x is 0 and y is ln of 2, we'd have e to the ln of 2, which is 2, plus ln of 2 times cosine of 0, which is 1, so 2 plus ln of 2. What's in the denominator? Well, we got 0 times this, so that's part 0. We got 0 times this, so that part 0, so it's just 1. So it's negative of 2 plus ln of 2 over 1. So that is dy dx at that point. That's actually the slope of the tangent line to this. The graph of this curve, whatever it may look like, has a tangent line. I guess it would be y minus ln of 2 equals this slope times x minus 0. Try doing it this way, the way you learn in Calc 1, and it's a little bit painful.